Okay. Thank you. I'm very honored to be the first speaker. Thank you all for getting up early to come to my talk. When I was starting my research career, we were taught to make the first sentence, we only consider graphs without loops and multiple edges. Some of us still write that. But when you think about it, sorry, I should have said that these are, interesting. So I don't really have a pointer, but it doesn't matter. These are my co-authors. There are a bunch of papers I am mixing up into this common theme. It's not common to give a talk about loops, right? So I wound together several talks and some papers from the literature. When you think about it, often graphs do have loops. Any intersection graph will naturally have loops because if the adjacency is defined by intersection, then every set intersects itself. So an interval graph really should look like this, right? You have a set of intervals, and two are adjacent if they intersect. So one intersects one, and therefore there should be a loop, and so on. On the other hand, there are versions of interval graphs which naturally don't have loops. I say a graph is reflexive if the adjacency relation is reflexive. So if every vertex has a loop, then the graph is reflexive. If no vertex has a loop, then graph is irreflexive. But in general, some vertices will have loops and others don't. So if you have two families of sets, and you only define adjacency for a member of the first family against a member of the second family, then this naturally will not have loops. And in some cases, like these two-dimensional array graphs, in fact, these two families, the horizontal arrays to the right and the vertical arrays upwards, the two members of that never intersect anyway, so it doesn't really matter. So I have two families. The red intervals form the red vertices, one part of the partition. The blue arrays form the blue vertices, another part of the partition, and they are adjacent if they intersect. Now, for a number of reasons that I will maybe touch on, I've perceived these two examples as being very closely related. I've come to believe that the two-dimensional array graphs are somehow bipartite analogs of interval graphs, more so than the well-known interval bigraphs. And so in a way, you should carry this as a theme of the lecture. We are looking for what is similar to those two classes. But here is another example. You all know the definition of a dominating set. You have a set of vertices such that everything outside of it is adjacent to something in the set. And there is a related concept of a total dominating set where also the vertices in the set have to have something adjacent to them from the dominating set. These two also feel like somehow that should be the same thing, right? If every vertex has a loop, then we are in this case. The vertex can dominate itself. If no vertex has a loop, then maybe we need to, if every vertex has a loop, then this definition gives me this. And if no vertex has a loop, then maybe we actually have to dominate. So what if some vertices have loops and others don't? There's a version that's common to both. Another nice example is the game of cops and robbers. You probably know the game. A robber puts itself on a vertex. A cop puts itself on a vertex, and then the robber puts itself on a vertex, and the cop has to capture the robber by stepping on him, and the robber wants to escape. And cop wins if he can capture the robber, robber wins if he can continue escaping. And there is also a second version of the game. In the first version, everybody can either stay or move. And in the so-called active version, you have to move. You cannot stay on the same vertex. Well, again, this is the version where you have loops. Every vertex has a loop, and so there is only one version, and that's this one. This differs by having a loop at every vertex. This doesn't have any loop. And you might have a version where some vertices have loops and other vertices don't. So one of the earlier papers that explicitly consider this version with possible loops, where some vertices have loops and others don't, is a paper of Brightwell and Winkler, and it deals with dismantleable graphs. So a graph is dismantleable if you can reduce it to a vertex by folding. And you fold U to V if the neighborhood of U is included in the neighborhood of V. And so they consider the graphs with possible loops, and this is their list of small dismantleable graphs with possible loops. So I don't know, let's say in this example, you can dismantle this vertex here because its neighborhood, which is just this, is included in the neighborhood of this vertex, which is both these vertices. So you dismantle that, and then you can dismantle this, and you have only one vertex, and that's dismantling. They also gave examples of graphs that are not dismantlable, and these are the small non-dismantlable graphs. And in fact, these are the minimal non-dismantlable subgraphs. Here you cannot fold anything in these examples, right? Well, think about cops and robbers played on this graph. Of course, the robber can put himself against, kind of opposite to the robber can put itself opposite to the cop and continue escaping, following the direction that the cop is chasing him. And in fact, these two concepts are related. Winkler and Brightwell have proved that in a graph with possible loops, the cop can win if and only if the graph is dismantled. It's not a complicated proof. It's a nice, in fact, nice exercise, but it shows that with the right concepts, the version with possible loops fits naturally. Now, just in case some of you are working on the active version and don't recognize the examples, the active version that seems to be more prevalent today has a small twist from the active version that Brightwell and Winkler considered, and that is if a robber jumps onto the cop and there is no loop, the cop has to move. So it's not considered capturing the robber, while some people consider that already end of the game, the robber jumped on the cop. But that's the only difference. All right, so let's think about another problem, and that is homomorphisms to a fixed graph. So you have a fixed graph H, and you have an input graph G, and you are to decide whether there is a homomorphism, an edge-preserving, adjacency-preserving mapping from the vertices of G to the vertices of H. So for example, if the fixed graph H is a complete graph, I'd say a triangle, then a homomorphism to a triangle is just a tree-coloring. Adjacent vertices must get different colors. Okay, so that's an example of what this homomorphism problem is like. And so almost 20, 30 years ago, Neschetschil and I proved that this problem is polynomial when H is a bipartite graph and is NP complete otherwise. And this has an interesting history I will talk about in the last lecture of the conference. But let me bring it in here as well, because when we prove this theorem, this is how we formulated, and this is how I discussed it with Thomas Feder, who plays a role in the talk tomorrow. But when he wrote it down, he wrote it this way. So there is a small difference. I consider only graphs, and he considers graphs with possible loops. And then I have to add another exception The difference between the two theorems is only in the trivial observation that if there is any loop anywhere, then a constant mapping to that loop is a homomorphism. So there isn't really a scientific difference between the two, but there is a huge psychological difference. And Thomas Feder used this formulation to compare this theorem with another theorem he knew, which is the Schaefer dichotomy of Boolean satisfaction problems. So Schaefer considered some generalization of problems like 2-SAT, 3-SAT, and so on. There is a general formulation that involves a system of relations on two-element sets. And I will discuss that on Friday. You will see that it includes examples like 2-SAT and 3-SAT and 1 in 3-SAT and all those, and more general problems. And he classified these into polynomial NNP complete, just like we have classified it here. And the three polynomial cases are when each of the relations contains an all 1 vector or an all 0 vector. Those are the situations where you can assign true to all variables and satisfy all constraints, or you can assign false to all variables, satisfy all constraints. And that is really the same spirit as the loop here. You just have a constant mapping. So constant mapping polynomial, constant mapping polynomial. Then what about the bipartite? How does the bipartite algorithm work? Well, coloring by a bipartite graph is the same as a coloring by an edge. So you give some vertices A, then anything adjacent to them must get B, and anything adjacent to them must get A, and so on. And how do you solve 2-SAT or horn-closed question? No. How do you solve these horn-closed examples? The horn-clauses are conjunction of disjunctive clauses which have only one, at most one negated variable. Right? So if all the assumptions are false, then, if at least one of the assumptions is true, then the conclusion is true. So you propagate again. All these problems are solved by propagation, just like bipartiteness. So this is similar to that. Now, in the case of satisfiability, there is a third possibility, which brings in algebra, some kind of algebra, linear algebra or something, that we don't have in undirected graphs. But nevertheless, Feder looked at these two cases and said there is great similarity. He formulated a conjecture I will talk about tomorrow, and how that proceeded. So again, it was just a psychological advantage, but the loops played a role here. So let me come back to interval graphs and trying to get from interval graphs to these two-dimensional array graphs. So one thing that interval graphs have is an ordering characterization. Now I want to mention one that is not exactly the one you're probably familiar with. So let me say it slowly. It's a linear ordering of the vertices, so that when you have two edges joining vertices in opposite order, then the smaller pair must be adjacent. It's best seen in a picture. So if I have an edge uv and an edge u prime v prime, but in the ordering u precedes u prime and v prime precedes v, they're crossed. If they cross, then the bottom line, the smaller two must be adjacent. It's not allowed that the small two are not adjacent. Some people call this the X underbar property. If you have an X, you must have the underbar, right? I think I have a proof, at least giving intuition why this ordering characterization, and so I'll prove one direction. Suppose that suppose we have an interval graph, an interval representation, and we order the vertices by their left endpoints. And suppose that this happens, uv is adjacent, u prime, v prime cross it, and the bottom pair is not adjacent. So if u and v prime are not adjacent, then one precedes the other, the intervals, and without loss of generality, say u precedes v prime, but V begins later than V prime. So U and V can also not be adjacent. U and V cannot be adjacent, but here they are not adjacent. Okay? The converse is also true. But if you think about this proof, maybe you already see, but I want to point out that this uses the loops, because another way of U and V prime not being adjacent is that they're equal, right? But for me, if they're equal, they are adjacent. So this proof by saying U and V prime are disjoint and apart, that uses the fact that I have loops. So this characterization is only good if you allow the loops. Another way to describe it is in terms of matrices. I write down the adjacency matrix in that particular order. And then what this says is that I don't have a matrix which has 1 in a position like this, and here, and then no 1 here. This is 0. This is an asterisk. Regardless of what there is there, this is forbidden. So a sigma matrix is really 2 matrices, one with a 0 here and one with a 1 there. All right, so now let's summarize what are our characterizations of interval graphs in terms of ordering. An interval graph has a mean ordering, and the adjacency matrix can be simultaneously permuted to avoid these 2 sigma matrices. Can't hear you. Good question. So I can go back to Another way to formulate this is to forget about these 2 and to say if U is adjacent to V prime, U is adjacent to V, U prime is adjacent to V prime, then the minimum of U and U prime is adjacent to minimum of V and V prime. Why is that? Well, if they don't cross, then one of them is the minimum, it's trivial. And if they cross, then we have this condition. Okay? Yeah, so the min function is a morphism of this. Okay, so another characterization of interval graphs is in terms of forbidden substructures. The theorem of Laker-Kerker and Boland explicitly listed families of induced forbidden subgraphs. For future reference, let me draw the smallest version of this graph. So the fan here, there is a fan, right? Could be just a triangle. So then this kind of net is a version of the smallest version of this graph. This is one of the forbidden subgraphs. You probably know the Laker-Kerker-Boland theorem in a different formulation, and but actually this is the one that they started with, and then they noticed that in proving that all these are forbidden, they always use the same kind of argument. They focused on 3 vertices, and they said you can go from one of them to any one of them to any other without coming through a neighbor of the 3rd vertex. So this is what they called an asteroidal triple. And in fact, it turns out that equivalent to this is a characterization of interval graphs in terms of the absence of asteroidal triples and induced cycles C4 and C5. Why do we worry about C4 and C5? Well, if the cycle is long enough, you have an asteroidal triple, but if it's not long enough, 4 and 5 don't give you 3 vertices. So, by the way, why is this condition necessary? If you have 3 intervals that are not adjacent, then one is in the middle, and any path joining the outer 2 intervals must intersect the middle intervals. It's kind of a continuity condition. So I want to introduce a new additional forbidden structure characterization for interval graphs, which we call invertible pair. UV is an invertible pair in a graph if there are two paths of the same length from, or walks I should say, two walks of the same length from u to v and from v to u, where the slanted edges are missing. So the first v is not adjacent to the second u. The second v is not adjacent to the third u, and so on. And then you have a similar pair of two paths of two walks of the same length, but possibly different length, and those two, where from vu you get to uv. And here is the argument that this is a forbidden structure for interval graphs. I claim that if you have an invertible pair, then you cannot have a mean ordering, because suppose in the mean ordering v is ordered before u, then this vertex must be ordered before that vertex. Otherwise, there would be two edges crossing with the bottom edge missing. So if v is below u, then this is below that, then u is below v. Well, that's contradiction. But maybe u is below v. If u is below v, blah, 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 then v is below u. That's also a contradiction. So there is no mean ordering for this graph. All right. So summarizing then, we have all these equivalent conditions for a reflexive graph which has a loop at every vertex, to be an interval graph. So we are now still aiming towards two-directional ray graphs. But those have no loops. So let's take a more general view and say, what about graphs that have some loops and others don't? Some vertices have loops and others don't. So we thought maybe the right definition of this concept would be through the ordering characterization, mean ordering, or maybe equivalently in terms of matrices. So what does a matrix look like for a graph with possible loops? Well, a reflexive graph has diagonal of 1s, irreflexive graph has a diagonal of 0s, and general situation is the diagonal is arbitrary, some 0s and some 1s. But nevertheless, the concept of not having a sigma matrix is well defined. And so let's look at the class of graphs which have a mean ordering in this sense. The adjacency matrix can be simultaneously permuted to avoid the two sigma matrices. Turns out that this is already been studied. It's the complement of a class that's been called the threshold tolerance graphs. So a graph is a threshold tolerance graph if you can assign to each vertex a weight and a threshold, and two vertices then are adjacent if the sum of their weights exceeds at least one of their thresholds. Okay? Now, I claim that we are looking at a complementary class. So let's reformulate this in the complement. It turns out that there are two linear transformations that produce from W and T another pair of functions, L and R. And the condition is nicer if we express it in terms of L and R. And the condition then is, in the complement of threshold tolerance graph, which we call the Coty-T graph, two vertices are adjacent if the L of u is smaller than or equal to the R of v, and the L of v is smaller than or equal to the R of u. This condition will sound familiar to many of you who worked on interval graphs, because in fact interval graphs have this property. If you have an interval graph, then you give the left endpoint the right endpoint, and let's read this in the negative. Let's say when they're not adjacent, if and only if this is false. So two intervals don't intersect if and only if one begins after the other ended, or the other begins after the first one ended, right? So this is the natural condition for an interval graph. But I now claim that this is also the natural condition for graphs without loops. Except it looks like there are some extra letters. This line is a little longer. And so interval graphs also have the property that the left endpoint precedes the right endpoint. And I'm eliminating that. So these are kind of interval graphs in which intervals can begin after they ended. And so this is how these have been studied. This is just one of the references. It's actually a popular subject. So there are intervals that are regular intervals that go from left to right, and then there are these weird intervals. Sometimes, people draw blue vertices and red vertices, and the weird intervals, the negative intervals, have a greater L than R. And we just notice that if we again read the definition as it is written, then if you have a blue vertex, LV is less than or equal RV, then both of these are satisfied, and so that vertex has a loop. V is adjacent to V. And if it's this way, then there is no loop. So here is an example of graphs with possible loops naturally arising. People who have studied these QTT graphs did not worry about loops. They didn't see this connection. And it's also useful for my example. I'll show you an example to translate these conditions into more readily understandable adjacencies. Two blue vertices are adjacent just if their intervals intersect. They're representing regular intervals from left to right, and adjacency is intersection. A red interval and a blue interval are adjacent if the red interval is contained in the blue interval, and two red intervals are never adjacent. That follows from the rules. So here is my example. That's this example, which was not an interval graph. How come it looks like an interval graph? Now that's because I forgot to draw the loops. This is where the loops are, right? But with the loops, here is the representation. The three blue intervals intersect. That's the interval part of it. And the red D is contained in the blue A, but in no other blue interval, so we only have this edge. And similarly for the other edges. So that's the primer on QTT graphs. But of course, I am saying that because I want to say that this is the class of graphs I was looking for. These are the graphs that have adjacency matrix, can be simultaneously ordered to avoid the sigma matrices, and therefore they admit a min ordering. And similar to that min ordering equivalent characterization by invertible pair, this also has a characterization. This is what an invertible pair looks like, except I can have a repeated vertex VV or AA if it's a blue vertex, if there is a loop on it. But I cannot repeat a red vertex. Okay. All right. So this is what we have concluded so far about this min ordering as a tool. A graph with possible loops has a min ordering if and only if it's a QTT graph, and more restricted if you have a graph which has all loops, a reflexive graph, then it's an interval graph. Now, before I get here, I want to say that, remind you that we were looking for a version, or irreflexive version. What is the irreflexive version of this? What if there are no loops at all? Well, those are red vertices. They can have no edges among them at all. So this unfortunately doesn't give me two-dimensional ray graphs. The only irreflexive graphs with a min ordering are independent sets. So it seems that we failed to, we shot something, but it's not the one we wanted. It's not the two-dimensional ray graphs. And to see how to bring the two-dimensional ray graphs in, we have to step back even further and consider digraphs. So what about digraphs? Well, matrices that we considered so far, the adjacency matrices, were symmetric matrices. So throw out that assumption. Suppose we just look at any 0, 1 matrix. Now the diagonal is arbitrary, doesn't have to be symmetric, so we're just looking at an arbitrary 0, 1 matrix. The first case that we looked at is the case when the diagonal is actually all ones. So we have a reflexive digraph. An arbitrary digraph, but every vertex has a loop. And there we characterized the matrices or the digraphs which have a mean ordering, and they turned out to be an interesting subclass of interval digraphs called reflexive, called adjusted interval digraph. So those are precisely the digraphs that have a loop at every vertex and have a mean ordering. And they are defined just like any other interval digraph. There is a general definition of interval digraphs due to Doug West and his collaborators and students, maybe Sandeep Das and some other students, or at the time some other colleagues were involved in this definition. That class is a little bit too general. But if you insist that the representing intervals start in the same vertex, they're left adjusted, they start from a common vertex and then go to the right, then this gives the right concept. Notice that these digraphs automatically have loops because the left endpoint is common to both intervals, so they intersect. So every vertex has a loop. So this turned out to be a good class of digraphs, generalizing interval graphs, and they can be characterized by the absence of invertible pairs, and they have similar obstruction characterizations like Laker-Kerker-Bolen, and the geometric representation is also kind of similar like interval graphs. So this is a successful extension of interval graphs into the world of digraphs, but it still doesn't touch the loopless, the irreflexive case. I wanted to mention an open problem. There is a now order n cubed recognition algorithm. This was our algorithm, and the Japanese computer scientists recently lowered it to order n cubed. But we don't have linear algorithms for recognizing these digraphs, even though they're very analogous to interval graphs. They should have a nice order m plus n recognition algorithm. I think it's a nice problem. All right. So I have kind of had a theme of trying to generalize interval graphs. And I want to say that the desired generalization is this green garden inside the jungle of graphs. So digraphs, this big rectangular digraphs, those that are symmetric, so they're undirected graphs, form the left half. These are not symmetric. Those that are reflexive, every vertex has a loop, form the top half, and those that don't have loops everywhere form bottom half. And we have seen some examples here. If you look at reflexive, then we know that the garden, that nice generalization of interval graphs, are these adjusted interval digraphs. And if you look at the left rectangle, those are symmetric, undirected graphs with possible loops. Those were the complements of threshold tolerance graphs. And the common intersection are precisely the interval graphs. But I still don't know what is the whole green space. And of course, the natural expectation would be that I should say those are the digraphs that have mean ordering. But when we first realized this, we had three obstacles. There was no geometric representation of these. The generalization of intergraphs should be some kind of intervals or some kind of geometry. We didn't have an obstruction characterization, and we didn't know whether this class is polynomial or not. And so all these things have now been solved. And if I have enough time, I'll tell you about it. What am I doing? 10 minutes. 10 minutes. Okay, wow. Okay, so at least let me give you the generalization, because it's kind of nice. We look at the mean orderable graphs and compare the interval graphs with the desired generalization. And we characterize the interval graphs in terms of functions and inequalities, and had this condition that the intervals are regular left to right intervals. Then we eliminated that and we got what we wanted. So that's the program I want to do for digraphs. I write the adjusted interval diagrams in forms of inequality. There is one common left endpoint, and then there is the right endpoint of the first interval and the right endpoint of the second interval. And then I express the adjacency, the intersection, in terms of similar inequalities as I have before. And so you would guess if you skip that line, you should be okay. And so that's what we tried. It's kind of mechanical, taking analog, starting from the adjusted interval diagrams and defining what would be maybe vertices with possible loops. That's what we came up with, and that in fact turned out to be the right answer. These new digraphs, signed interval diagrams, are precisely those diagrams that have a mean ordering. So this is the geometric representation of the mean orderable graphs. It's like the adjusted interval diagrams, but some intervals go to the right and other intervals go to the left. You can have both going to the left, one to the right and one to the left, both to the right, or whatever. In adjacency is defined in similar ways as for undirected graphs. And so this is the class of mean orderable diagrams or signed interval diagrams, the geometric representation. They turn out to have a forbidden structure characterization that is similar to an invertible pair, but a little bit more complicated. Invertible pairs are not enough. You might need invertible triples or quadruples, and they are similarly shown to be necessary and also sufficient. So the green garden is mean orderable diagrams or signed interval diagrams. And now we can finally see where the two-dimensional ray graphs come in. If you focus now on bipartite digraphs, you get the right concept. So what are bipartite diagrams? Well, they just have all edges going from one part to the other. So for this concept to fit into this framework, to see this as a generalization of interval graphs, I must view this as a directed graph, a directed bipartite graph, with all edges going from the red vertices to the blue vertices. But that really is just a conceptual difference. I don't usually draw the arrows. So this is how two-dimensional ray graphs fit into that green garden. In fact, I have zoomed in here. This is a zoomed in figure of that big world of diagrams. So big matrix or the big array, something like this. I have divided the top half were reflexive, the bottom half were irreflexive, the bottom half were not reflexive. But the bottom half itself is divided to those that have no loops at all, or those that have some loops and not others. So this is the very bottom of that rectangle, graphs that have no loops at all. Similarly, this is the very right-hand side of the rectangle, those graphs that are antisymmetric. You never have a diagonal. When you have one edge, you don't have the opposite edge. So that's this rectangle. Within that, there is still a smaller region of bipartite digraphs. Those are bipartite graphs with all edges being directed from one part to the other. In that region, my green garden intersects it in the two-dimensional ray graphs exactly. So those are precisely where two-dimensional, and in this way they are then the analogs of interval graphs. There is also an invertible pair characterization, and I will skip these because I want to tell you about very quickly about another class of graphs where generalizing from loops gives us an interesting concept. So strongly chordal graphs. Do I have time, or should I just skip this whole part? Okay. Graph is strongly chordal if it has a strong ordering. And the picture for a strong ordering is in matrix language. If you have the two crossing edges and the bottom edge, you must also have the top edge. It's forbidden for the top edge to be missing. Now, these matrices play a role in if the constraint matrix of a linear program has this property, doesn't contain the gamma matrix, then the linear program can be solved by a greedy algorithm. It's the result of Allen Hoffman. And so this turned out to be interesting, and graph theorists have studied strongly chordal graphs. They are again best viewed as reflexive graphs. The diagonal is all ones. And there is a forbidden subgraph characterization in terms of induced cycles, so they are chordal. And in addition to this, they don't have these induced trampolines. There is a parallel class of chordal bigraphs. Chordal bigraphs have a pair of orderings, one on the top vertices and one on the bottom vertices. And they have a similar characterization by forbidden matrices, except this is not the adjacency matrix, this is the bi-adjacency matrix. These are the top vertices versus the bottom vertices. And this matrix is forbidden there. They have a similar forbidden structure characterization. And what we were after, these have no induced even cycles of length greater than 4. So, of course, graph theorists perceive that chordal bigraphs and strongly chordal graphs are very similar, and there are translations of how to change one into the other, and some theorems translate, others don't. But we were looking for a common generalization, because chordal bigraphs don't have loops, strongly chordal graphs have loops. What would be the concept with possible loops? And we define it again the same way through the ordering characterization. The matrix should be forbidden. So for reflexive graphs, we get the strongly chordal graphs. For irreflexive graphs, we get the chordal bipartite graphs. It turns out that odd cycles are automatically forbidden. And so it only talks about bipartite graphs, and you get the right concept. So maybe the one last thing I would like to show you is a characterization by forbidden induced subgraphs. Because now I'm looking at a graph with possible loops, and that has the same ordering characterization by avoiding the gamma matrix. It also has the property that the adjacency matrix is totally balanced. It doesn't have a cycle submatrix. Cycle submatrix has 2 ones per row and column. But this is our forbidden subgraph characterization. There's more to it. This is just the first half. The black vertices have loops. The white vertices have no loops. So here are the cycles. These are the things that are forbidden for chordal graphs. These are the things that are forbidden for non-bipartite graphs and for bipartite non-chordal bigraphs. And then there are these additional things where you can have 1 loop or 2 loops, or 1 loop with a fan, or 2 loops with 1 fan, or 2 loops with 2 fans, or generalizations of trampolines. You take the regular trampoline and you can skip some of these degree 2 vertices. And if you skip enough of them, you can join 2 of them, and you can join 2 pairs of them as long as the pairs are disjoint. But that's all you can do. It's a nice characterization of these graphs. All right. So to conclude, I will just come back to the dominating set problem. Now remember, we decided that there is just one version of general dominating set, which is this definition. And then vertices which have loops dominate themselves, which includes this definition if every vertex has a loop. So this is the problem I would like to solve in this new class of graphs. Because the strongly chordal graphs were partly invented to find a class of graphs in which the dominating set problem is solved in polynomial time. This problem is NP-complete for chordal graphs, but polynomial for strongly chordal graphs. And this problem is polynomial for chordal bipartite graphs. So you would suspect that this problem should be polynomial for this new class of strongly chordal graphs with possible loops. And this is what we actually accomplished. So we have a linear time algorithm to find the smallest general dominating set in a strongly chordal graphs with possible loops. It's a very simple one-pass algorithm. I'm not going to talk about it, but I'll leave it here. I apologize if I've taken too long. Thank you.